to refresh your memory, the standard form of a polynomial. So the polynomial is defined as the one that is computed through multiplication, addition, subtraction, multiplication, and no division. And then there's a standard form of it, which is here. Okay, the power is going down. The standard form of representing as a combination of a polynomial as a combination of powers. Okay, and then that where we are now is we're looking at factoring polynomials, and that's a new factored form of a polynomial, the meaning of which is, as we have discovered, all of these factors will correspond to, well, not all of them, but the linear factors will correspond to x-intercepts. Okay, so you can see that with the quadratic polynomial, something more familiar is if it is factored into separate x plus 1, x minus 1, two separate, different, rather, factors, it means that the two x-intercepts are different, and so that's the picture of the parabola. If it is the same factor, means the same x-intercept, which means there's only one x-intercept, which means that the parabola touches the x-axis. And if there are no factors, there are no linear factors, so you cannot further factor the quadratic polynomial, which happens when the discriminant is negative. Then there are no x-intercepts, and it hovers either above or below the x-axis. So very similar things happen to general polynomials. So they also have could have all of these cases only multiplied by the number of the degree. Okay, so you can still have linear factors. You can have up to n linear factors. That's what this theorem is about. And then you can have repeated factors, in which case you might have touching of the x-axis rather than crossing it. And then it's still possible there are no x-intercepts, or there are factors that do not produce any x-intercepts. So you just that x squared plus 1 is such a factor. So as you can see, well, this one is I want to see it again, a factor. The y factors correspond to x-intercepts. Okay, so factors and x-intercepts. Well, by factors I meant linear factors. Linear factors correspond to x-intercepts, quite literally. So it is x minus x1. X-intercept is x1. Okay, so that's the big story here. Okay, so y, if we have x minus x1, well, there is this rule of numbers that probably worth remind you about. It's called the zero property. Zero factor property. So it has nothing to do specifically with polynomials. It deals with numbers. So what we're saying here, if a times b is equal to 0, then either a or b is equal to 0. Okay? So you cannot multiply two numbers that are not, neither one is 0, and end up with 0. Okay, so it's something that we know from early on. And there's a converse too, which is a converse. So if a is equal to 0 or b is equal to 0, then a, b is equal to 0. Okay, so like that. Zero factor property. The only benefit of writing it up is that it's in front of you, so you would forget. But otherwise, you certainly are familiar with this property. Probably have used it a lot. It is inevitably come up every time you solve an equation when you factor it. So that's why factoring polynomial or anything else, not necessarily polynomial, will also correspond to finding solutions. Okay, so as long as you when you're solving your equation, you put in the right hand side you put 0. Okay, so x squared is equal to 1, that's one thing, but if you put x squared minus 1 equal to 0, then the question becomes about factoring. It's not about, this is a convenient form if you already know the answer, but otherwise, putting 0 in the right-hand side is always a big benefit, then the question becomes entirely about factoring. So it is x minus 1, x plus 1 equal to 0, right? And then you know that either one or the other or both would have to be equal to 0. Okay, so, and then that applies to quadratic polynomials, it applies to a polynomial of any degree. Okay, so then if you look at, once again, x minus x1, x minus x2, nth degree polynomial, x minus xn, if it is equal to 0, we're looking for its x-intercepts, then x1 could be equal to 0, x2 could be equal to 0, all of these are the possibilities. If you like, I'm sorry, that's not what I meant. X could be equal to x1, x could be equal to x2, x could be equal to xn. What are these? These are the solutions of the equation on one hand, and on the other hand, these are x-intercepts. Okay, so in other words, this is what we're looking at. My graph might cross the x-axis many times, and these will be here, x1, x2, x3, x4, and so on. What you might face, let me continue on, what we might encounter, we might encounter something like this. So this is x7, but it is special, as you can see, touches the graph, does not cross it. So what does it mean when it is an x-intercept, it is a solution, but we look at the graph and it does not cross it? What does that mean? It simply means that, as an example, the factor is the factor that corresponds to, so say this one, x minus x1, that's the factor. This one is x minus x2, another factor. And this might correspond to x minus x7 squared. Okay, so as you can see, it does not, if you look at separately from everything else, x minus x1, if you look at the factor separately from everything else as a quadratic polynomial, then it is a complete square. And what about complete squares? They have to be larger than or equal to 0. So they only touch the x-axis. Okay, and then if that part, that complete square is a part of a factoring of a nth degree polynomial, it serves the same purpose. Around that point, nothing else matters. Only this factor, which happens to be a repeated linear factor. So even though the x-intercept is there, there is no crossing. The function cannot become negative, and there is no crossing of the x-axis. So there is only touching. So that's the analysis that we have to learn how to do. The answer is fairly simple. It is you have to count what is called the multiplicity. So the multiplicity, how many times a particular factor appears. 1, 1, 1, 1, 1, and this one is 2. So what determines the way the graph crosses the x-axis at that location is the answer is whether it's even or odd. Okay, so even multiplicities produce touching, and like this or like that, while odd multiplicity give you crossings, either by straight line or it doesn't matter from below to above, doesn't matter like this. So these could be 3. I mean, if you take x cubed, it has x cubed. It is actually factored polynomial x minus 0 cubed. So in other words, this is a cubic polynomial, degree 3. It has 3 factors, all linear factors. The x-intercept is only 1, 0, but its multiplicity is 3. It is either you can call it a root or x-intercept of multiplicity 3, so which is odd, which means that it crosses. Okay. Alternatively, x squared is x minus 0 squared, degree 2, x equals 0 is a root, but of multiplicity 2, which is even, so it's just touch. Okay, so that's roughly how analysis of this works out with the with polynomials of any degree. So as long as you are able to factorize it and put like you did common terms in elsewhere, common terms combined together. Same with factoring. If the factors repeated themselves, you combine them together so that you will find the multiplicity. If you know the multiplicity, you will know how the graph will cross how it crosses the x-axis. Okay. So as another illustration, let me do this illustration. We can plot with that help. If the polynomial is factored, we can plot anything as complex as you like in this manner. So let me take this polynomial. Okay, so even though it looks factored, we need to extract linear factors from it. Linear factors as much as possible. Okay, so well, let me put it one more here, like this. Okay, so that makes a lot of factors, but that's okay, I guess. So let me factor x squared here, and I'm left with x squared minus 9. Okay, here x squared minus 3 squared. The last one is it has no linear factors. It is called irreducible. So remember, just from your test, x squared plus 1 can never be equal to 0 as far as with real numbers. So which means that there can be no linear factors. Remember, every linear factor will give you a solution. It will be give you an x-intercept. So if you know that there are no solutions, that there cannot be no factors. So x squared plus 1 is it. We cannot do anything with it. The rest of them are okay. So x squared minus 9 actually is x minus 3x plus 3. So we can use that. Okay. Then this one is factored into what? It looks complicated. How about I just erase it? Okay. Just make our life easier. Okay, so this is my polynomial. Then it has been factored. All the terms are collected together, including multiplicity. So this is x equal, let me put it in a form that is more recognizable, x minus 0 squared. Okay, so then by just looking at this factorization, we can see x-intercepts. They are 0, 3, and minus 3, and none here, because it is not factorable any further. So you have these 3 x-intercepts. So it is where at these 3 points, my polynomial will cross the x-axis. The degree of the polynomial is, by the way, pretty high. It is in fact 6. So 4 and 2 degree is 6. If you multiply it out, you'll see the highest degree is 6. And it crosses the x-axis 3 times. It could cross up to 6 times, but this one only crosses it 6 times. Why? Because to begin with, because multiplicity is of x equals 0, multiplicity is 2. To begin with, that's how you lose already one extra intersection. And secondly, you have no intersection. The last one, the last term is irreducible, so it does not contribute anything to the two x-intercepts. Okay, so Okay, so then we already know what's going to be happening. Even multiplicity will give us a touch, and odd multiplicity will give us a cross. Okay, so so touch meaning it touches and goes back. That's what the meaning of a touching graph touching the x-axis. So if I try to imagine what it looks like, I plot these 3 points on my x-axis. So 0, 3, and negative 3. Okay, so these are points. I plotted them in orange. The whole graph will be orange. So these will already have 3 points on the graph of my curve. Okay. So the only thing is we're gonna connect them somehow. We just don't know which way. But let's pick one. So cross. The information is here. Let me repeat it. So this will be touch, cross, and cross. Unfortunately, that's not enough because we don't know if it touches from below or it touches from above. Okay. We also don't know if it crosses down or crosses up. Okay. To find out, we need only 1 point. We need only one extra point in order to the starting point. We need a starting point. So in other words, 1 point other than these on the graph. Okay, so that's not really that complicated. You just all you need to do is just pick an x and plug it in. X as long as it's none of these. So what can I pick? How about 1? How about I pick a 1 and then plug it in and see what happens. So then f of 1 is 1 to the 4th minus 9 times 1 squared. 1 squared plus 1. So what is it? It is minus 8 times 2 minus 16, if I'm not mistaken. 1 minus 9 times 2. Doesn't matter what the actual number is. The point is negative. Okay. So that extra point is has been found. If the point on the graph is 1, negative 16. It is on the graph. 1, negative 16. Okay, so that point that I just found is here somewhere. Okay, so that helps. That tells us the rest, almost the rest of all we care about the rest of the graph. Because now, starting from this point, I will, if I go to the right, I will eventually, where am I going to end up? I'm going to end up at 3 over there, like this. Remember that what the special thing about that is about polynomials. They made of its curve is one continuous curve. So it is like a piece of rope. So it cannot jump from one location to another, and so therefore, if we have 2 points next to each other, that's what it's supposed to do. Also important that it cannot cross or jump over the x-axis. There are no other x-intercepts between these 2 points, so I will go pretty much straight from one point to the next, and that's where I reach it. And then a comment at the bottom. I'll have to cross it. It says cross, so I cross. Okay, so we have a piece of the graph. Now I'm going to the left. From that point, I'm going to the left. Once again, there is no other way but to get to 0 here. But the difference is, if you look at the comment, it says touch. So it will not be crossing into above the x-axis. It will go back like this. Okay, so this is the way we're plotting it. It's going down, and then you can guess. Once again, there is no way as we're moving from right to left. At some point, we have to reach 3 and cross it. Okay. So that's roughly the graph of the function based entirely on the plotting of the polynomial. Okay. So on left and right, it will go to infinity, as we can presume. But this is a small scale analysis, finding the x-intercepts and finding out wherever it is located relative to those x-intercepts. So it crosses these two, and it does not cross the one in the middle. Okay? So that is how we analyze it. But the challenge is, of course, how to factor it. We're not gonna address that. There's really no. That problem has no solution. So factoring, we can factor quadratic polynomials with the quadratic formula. Remember, so once again, you find x1, x2, then xy minus x minus x1, x minus x2 will be the two factors. There is a cubic formula too. It's quite a bit longer. And then there is fourth degree formula, which takes a whole page. And there is no fifth degree formula. There is no fifth degree formula. There is no sixth degree formula. So as far as we're concerned, beyond certain level, factoring is not something that you can do by hand or with a formula or anything else. So it is pretty much just assume that somehow we have factoring, and then we can say something useful about it. Otherwise, we are pretty much stuck here. So, however, there is some theory behind it, behind this factoring that I want to explain now, and it is based on the on a big analogy. So factoring, but this time factoring is not entirely about polynomials, it's also about factoring numbers. Okay, so the analogy is between integers and polynomials. So the idea is that the analogy allows us to deal with something more complex, polynomials, by analogy with something that is simpler, and that is integers. So integer numbers, 1, 2, 3, 4, negative 2, negative numbers as well, and 0. And so not real numbers we have been dealing with for so long. But the analogy applies to only to integers. What's the similarity? Well, let's start with some basic things about integers, and that is what is a prime number? What is a prime number?
It can't be like divided
by
anything but 1.
Right, that's right. So divisible only by 1 in itself. Divisible only by 1 and itself. The point is that it cannot be further factored. Okay? So what is the divisibility? That's what divisibility is about. So 3 cannot be further factored, but 6 can be 2 times 3. So that is the idea. Is then you can see the similarity with what we just discussed. We are trying to factor polynomials, and we encounter the same problem, and that is what is a polynomial that cannot be further factored. So it is an irreducible polynomial. So it has no linear factors other than unless it is linear itself. So the standard example is once again x squared plus 1. Well, x plus 1 is a linear factor. You cannot further factor it. So this is an irreducible polynomial. Irreducible quadratic polynomial is x squared plus 1. Okay, so and that is the analogy. That is the similarity, and they behave in a similar way. And that is, but before we get to that, there is a fact about polynomials that we need to mention here. only linear and quadratic polynomials can be reducible. Or could be irreducible. So in other words, cubic polynomial can always be factored. Okay, it can be find other factors. I don't think I put it the right way. Let's just say it cannot be further factored. I think that's a better way to put it. Cannot be further factored. For example, the certainly x cubed minus 1 can be factored. It is x minus 1, and here I have x squared plus x plus 1. Okay, so fourth degree polynomial can be factored, even though they are not necessarily the ones that can have actual x-intercepts. So some of the curves, some of the polynomials might look like this, but it doesn't mean that they cannot be further factored. So only quadratic polynomials have this property that there is no further factoring of them. So for example, x to the fourth plus 1, okay, this polynomial has no x-intercepts. However, it can be further factored. Can be factored into quadratic factors. Okay, so I don't have the formula with me right now, but it can be further factored. So that's just the fact that this makes life easier, because when we talk about factorizations, then we will be using only linear and quadratic polynomials. But this is, well, let's do numbers first. It's called the fundamental theorem of arithmetic. And it says that every integer can be factored into the product of prime numbers. And this factorization is unique. Okay, so you certainly can rearrange the terms, but as long as you keep track of the factors, it is the same factors taken together, including the multiplicity. So if you repeat something, x minus 1, if it appears twice, then you count them twice. Okay, now what is the analog of the fundamental theorem of arithmetic that applied now to polynomial, and it is called the fundamental theorem of algebra. So it's very similar. Every polynomial can be factored into the product of irreducible polynomials. As we know, they will have degree 1 or 2 only, and this factorization is unique. Once again, up to the order of the factors. You can rearrange the factors, but the outcome will be the same. So that explains why that analysis that we just did is valid, because there is no other, this analysis over here, there is no other factorization. So once we found the factorization, this is it. We cannot try to put it back together and use some magic of mathematics and find another factorization. This is it. These are the factorization, and then you can certainly guess why it is the case, because if it is an x-intercept, it is an x-intercept. So in every x-intercept corresponds to a factor. Okay, so let me touch upon this complex area of complex numbers. So where do complex numbers come from? So that certainly takes a while to get used to them, and so we'd better start early with that. So complex numbers allow us to to deal with the factoring in a much more easier way, and that is factoring is always will be factored into linear factors only. Okay, so there won't be anything like x squared plus 1 cannot be factored. It is irreducible, but it's not the case if we're allowed to use complex numbers. So complex numbers are numbers that you haven't seen before if you have only been studying real numbers. So any kind of measurements, any kind of locations, quantities, anything that in real life that you encounter, every single thing are real numbers. Okay, at best, some of them are even you have to be integers, so even in the narrow class. But then there are complex numbers. So if you can start this way, integers. Then rational numbers, we're going to talk about that shortly. And then real numbers, bigger class. And then if you are feeling adventurous, then you add a new class of complex numbers. So once again, you will not encounter them in real life. So that's why. Anything you see in real life that you interpret mathematically is numbers. They are all real numbers. So what are complex numbers? The starting point is the root of the of that polynomial. X squared plus 1, x squared plus 1. So solve x squared plus 1 is equal to 0. We know that there is no such real number, but we say if we are really willing to, we say that we just add a new number that satisfies the equation. Add, meaning that we have real numbers, and then I take that number and put it here. Okay? Outside, clearly not a real number, but I just want something that satisfies this this equation. It's called, we use the letter I for it. I stands for imaginary. So this is my I. So to begin with, just one number that is not real, and it is all imaginary. And the only thing that we require from it to begin with is that I squared is equal to -1. Okay, so let's imagine that, or this is all we have to begin with. Then my polynomial x squared plus 1 can be factored into x minus I, x plus I. So the second thing required for this number, it will be that it can be, we should be able to do every algebra with this number just as with a real number. So we can add them, multiply, divide, and so on. Okay, to begin with, this is it. We have factored our quadratic non-unfactorable polynomial has been factored with the help of these imaginary with this imaginary number. So if you look at it, if I try to plug in, so this is my f of x. If I plug in I, f of I is equal to x minus I. Not x minus I, but rather I replace x with I. What do I get? I get I minus I times I plus I. So it is 0 times 2i, which is equal to 0. Okay, if I plug in negative I, the same thing happens. I have I minus I minus I, minus I plus I. I have negative 2i times 0, and it is equal to 0. Okay, so as far as we can tell, that number I indeed satisfies our inequality. The factoring is what we have we're getting in return. So every polynomial has exactly 2 factors. Every quadratic polynomial will have exactly 2 factors, even when there is no x-intercept. And we are not going to be confusing x-intercepts with roots of a polynomial, because after all, if we know the x-axis is the we also called it the real line, right? It is the real line, which means that I does not belong here. So even though we know that if we plug in I into our function, we get a 0, we know that that number will not appear on the x-axis. So that does not tell us anything new about in that respect about our polynomial. The x-intercept still there are no x-intercepts, so the graph remains the same. It is only at this point nothing but an algebraic trick. Okay, so I'll stop here and I'll bring the test next time.